Morning, afternoon, Algebra 2. Do you guys have your graphing calculator today? You're going to need it. Where's mine? Uh-oh. Oh, found it. Hey, you can see we're doing lesson 75. Graphing. Radical functions. Dude, they're like, oh, so like, bam, They're kind of actually, they're more like, dude, like that, the functions. So I'm going to start with a little bit of algebra behind these things. And then we'll start, I'll start drawing some pictures and explaining stuff. Okay, I'll give you all like algorithm about how to go about figuring these things out. Let's see, I'm just looking at my notes here really quickly, like how much of this we're going to end up doing. Right, okay, no problem. Whoa, earthquake, sort of. Okie dokie. I'm sorry about the lights there and being able to see stuff. Right here it says radical functions. And over here it says power functions. And I want to show you that these two things are inverses of each other. Maybe we could start over here on this side with power functions. Instead of doing x squared, which is our first power function, I just decided we would start with, we do it in general, x to the n. And that could be a squared or cubed or the fourth power or whatever. Doesn't matter. So here's the function for starters. And then I'm going to replace the f of x with a y. That was our first step of finding an inverse. And then I'm switching where x and y are in the equation. Okay, so that was our rules for going through and doing a function or an inverse function. So now my job is to solve for y, okay, in terms of x. So I take the nth root of both sides, and I'll get plus or minus the nth root of x equals y. Graphable, okay? There it is. There it's its inverse is a root function, okay? A rational. No, it's a root function. Whatever. Okay. Radical function. Or we can go over here and we can start with the radical function that I just derived, and I'll play the same game. I'll change f of x to y of that, and then I'm going to switch where x and y are in the equation, and I'm going to solve for y. So to undo this root, I'm going to take it to the nth power on both sides. The nth power will match that index, and we'll just have y equals x to the n. That's our power function. So as you can see, these two are inverses of each other. If you're going to graph these things, and you are going to, you're going to graph these things on your calculator, and you want to graph something like the basic parent function for a radical function, okay? You would have a picture like this. Start at the origin, and then it'll go like that. And that's it. They have the same basic shape, and they'll continue to increase, but at a lesser and lesser angle or slope as it goes. But it's always going to increase forever. Think of this. Another way to write this would be x to the 1/2. Okay? X to the 1/2. That's how we would write a square root. And over here we had, for our other function, we've got x to the 2. So you can see inverses here means something interesting when we're talking about powers and roots or powers and radicals, is that you take the reciprocal of that power and you've got the radical function. So x squared is that guy's inverse over there, and we know x squared is our friend, the parabola. Okay? Our friend the parabola. If we put these on the same set of axes, and I'll do that over here, put our parabola in here, that's what we're going to have right there. We only really get half of this function. Remember I had over here I had plus or minus. So technically, if I was to do plus and a minus, I would have another half of that function there. I'll just do it in a dotted line. And if I want to check visually for inverses, I'm going to put in the line y equals x. And that would go right there. Okay, so we can see, come turn, and I'm gonna like restrict this sucker to just that part of it. I can see that those two are reflections of each other, pretty close over the line y equals x. So visually, I can show you there. They are inverses. Line symmetry there, and they meet at the point, I think this is the point 1, 1, and they both met at the point 0, 0. That's where their answers would be the same. And then this won't curve up forever, and that won't curve out forever, but there they are. They're inverses of each other. Okay, let me erase this stuff. Hopefully you're writing that down, or you can go back 15 seconds and do that. Moving on. So if you recall, go back over quickly the process that I took. We would, if we were going to find its inverse, we could start with a radical function, something with a rooty thing in it, and then 2, we're gonna switch x and y in the equation, and 3 solve for y. That will give us our inverse function. You will also then, to verify, you will graph on the same set of axes with a y equals x line in there to check for graphically that they're inverses of each. Inverses, is that what you said? I said inverses is. Mooses, moosin. Another suggestion would be that you put that sucker on zoom 5. That would be, you know, zoom square. S-Q-U-A-R-E, square. That way you can see it a little bit better. It'll look more like an inverse if you do that. Right, let me show you an example of that process there. Again, write that process down. You can pause me and write down. I got to keep moving. It's almost so much time in a day. You know what I'm saying? What we're going to do, sit around and watch movies all day long? I don't think so. Let's start with this one. Y equals x minus 1. Then we're going to switch where x and y happen to be. And then we're going to solve for y. I'm going to do this by unrooting this. Okay, so we're going to have x squared over here. On this side, we're going to have y minus 1. And then we'll finish this off. There's its inverse. Right? X squared plus 1 equals y. So now you need to graph this, and you need to graph this on the same set of axes. And I'll leave that up to you to do that. I know you're smart enough to do that. Along with the line y equals x. So you probably have y1, and it's probably y2, and that was a 3, and that'll be your y3. Okay, graph them, take a look at them, see that they appear to be reflections of each other over the y-axis. Now you can go up to any power. That's why I started with a generalization of that problem of just having an n in there for an nth root or an nth power. Yes, indeed. So let me give you an example of cubic, or taking a cubed root. Let's start with y equals the cubed root of something something, and what its inverse would be. So I'm going to switch x and y, and then I'm going to cube both sides. X cubed equals y plus 1, and then I'm going to move that 1 to the other side. X cubed minus 1 is y. If you graph those on the same set of axes, I'll just show you on my on my drawing here what that would look like. It's this one up here. You get the wiggly line. I got my dotted line right down the center. And I got my functions labeled too. X cubed minus 1 is a squiggle that goes up. The cubed root of x plus 1 is a squiggle that kind of goes sideways. And if I tilt it this way, you can see these two are inverses of each other. You're welcome. All right, so that's pretty much the deal. Oh, we're getting a little like out of focus there. Either that or I need to get my glasses checked. Hey. Ah, that's a little bit better. Okay. Last thing is when you're gonna have a hard time finding an inverse, and that would be with something like this. Plus the cube root of x plus 2. Complex. Oh, I guess it's not finding an inverse. It's just having something that's like a higher version or a more complicated version of this type of setup. Go ahead and graph that sucker, okay? Graph it. You've got a square root here, and you've got a cubed root there. I'm going to graph on my calculator, and then I'll unpause. Okay, I did it. If you don't remember where to find the how to do the cubed root of something, remember you can go alpha and then F2, and up there in the list of things is number 6 as x root of the thingamabobber. So you can pick number 6 if you want a cubed root or whatnot. Anyway, this is my friend used to say anywho. There you go. There's the equation, and then there's the graph of it. It's not super exciting, is it? It's a little curvy thing. So you'd have to just graph that sucker. And yeah, yep, there you are. There's going to be some question about architecture. And so one of the things you're going to need to do, and I'll leave a link in the email, is go watch Matt Parker's Stand Up Maths channel. He had a time where he went to Sydney. He is Australian, after all. Where he went to Sydney and he was looking for parabolas. Okay, he's looking for parabolas. The Sydney Opera House is that kind of cool, weird geometric shape. He goes and he analyzes that. He's looking for arches in the bridge. He's looking for all kinds of stuff. So anyway, it's called Sydney, the Unsuccessful Hunt for Parabolas. It's about 5.5 minutes. I'll send you the link to the number file video thing, and you'll just do a number file thing on Matt Parker's thing instead. That's it. If you want to do a little bit of math chatting, just send me a text or an email message, and we can work that out. And yeah, that's all for now. See you later.